I'm sure somewhere in your household you can find a symbol on a variety of plastic items. But what do they mean? Well, each number corresponds to a specific type of plastic and is used to sort the plastics for recycling or waste. But the two plastics we'll be concentrating on are HDPE and LDPE. What do they stand for? HDPE stands for high density polyethylene and LDPE stands for low density polyethylene. As you can see, they both belong in the family of polyethylene products. So what differs them from each other? Well, some common traits they share are they are both thermoplastics, meaning that they can be melted and reformed as much as you want without any change to the chemical structure or composition. They have relatively high melting points, they're excellent electrical insulators, they have low water absorbance, they're solvent resistant, low cost, and most importantly, FDA compliant, meaning that the US Food and Drug Administration has cleared it for contact with food and drugs. What specifically differs them from each other is the name. HDPE has a higher density than LDPE, but more specifically, HDPE has a density of 0.935 to 0.960 grams per cm cubed, while low density have a 0.91 to 0.925 grams per cm cubed. But the density is minute, I hear you say. That is true, but the true reason that they differ from one another is the way each plastic is chemically structured. HDPE and LDPE are both organic compounds, meaning that they include the element carbon in their composition. This is unique as the carbon molecule allows a compound to form unique structures or chains. HDPE has a linear structure, meaning its molecules are very straight in nature. Think of blades of grass, perfectly straight, no branches. On the other hand, LDPE has a branch structure, meaning that past the primary chain of molecules, there are branches that branch off in random directions. These give the compounds some unique properties. For example, due to HDPE's linear structure, it allows the chains to pack closer together than if they were branches, and vice versa for LDPE. This packing density gives the structure unique properties. Due to the denser packing, HDPE has stronger dipole-dipole forces and has a more crystal-like structure. The properties of HDPE having greater tensile strength than LDPE, and is also stronger, more rigid and stiffer in nature. LDPE is the opposite of HDPE. Its low density causes lower strength, stiffness, and lower temperature resistance, but its flexibility allows it to weather more impacts and is transparent when drawn into a film. But what does this mean for the uses? Well, being FDA compliant and a thermoplastic, it makes it perfect for when packaging food. For example, HDPE is used in milk jugs, while LDPE is used in disposable wrappers. HDPE is also suited for injection molding due to it being a thermoplastic, where it allows the creation of large products due to its excellent weight to strength ratio, whereas LDPE allows it to be used in thin films, such as waterproof linings to cardboard. Both have excellent chemical resistance, allowing them to be used in labs. LDPE can be used for squeezable bottles, while HDPE can be used for storing chemicals. Both can be drawn to pipes for all purposes. HDPE's tensile strength also allows it to be used for ropes and nets, while LDPE's flexibility allows it to be used for insulating products. All in all, each plastic's products are unique in every way. Now you know what differs the plastics, it's time to ask what they are. To understand polyethylene, we first have to understand the terms monomers and polymers. According to the Oxford Dictionary, monomers are a molecule that can be bonded to other molecules to form a polymer, and a polymer is a substance that has a molecular structure consisting chiefly or entirely of larger numbers of similarly unit bonds bonded together. But this means absolutely nothing to you and I. So it's better to think of monomers like a Lego brick, a singular building block, and polymers as a collection of monomers that create the Lego corner cafe and hotel. In our context, our building block is the ethene molecule, an unsaturated organic compound, or better known as an alkene, and a polymer is the collection of ethene monomer, polyethylene. But how do we get ethene? First, we must find a long saturated alkane chain. This is usually in the form of crude oil or naphtha. The chain then undergoes a process of cracking. Cracking is, according to BBC Bitesize, a reaction where larger saturated hydrocarbon molecules are broken down into smaller, more useful hydrocarbon molecules. An easy way to crack the chain is to place a chain under a temperature of 800 degrees Celsius. This splits the chains into two products. Ethene is what we need, and a residual alkane chain. Now that we have ethene, how do we get from here to polyethylene and its products? This depends on the plastic we're making. For LDPE, it undergoes a process called radical polymerization. Essential conditions are very high purity ethene, very high pressure, about 1000 to 3000 atmospheres, moderately high temperatures, 420 to 570 Kelvin, and an initiator, usually in the form of oxygen. Radical polymerization works by breaking the double bond and allowing it to bond with other free radicals. This forms chains. But sometimes a H bond can break, causing branches. This final product is a chain of polyethylene, with branches coming off in random directions. In industry, this process is about the same. Ethene is compressed, then heated, and then reacted into polyethylene, where the molten polyethylene is extruded into pellets and shipped. For HDPE, this is much more complicated. The essential conditions are different to form the linear structures. The conditions are relatively low pressures, about 10 to 80 atmospheres, relatively high temperatures, 350 to 420 Kelvin. Ethene is mixed in with hydrogen and utilization of a catalyst. The Phillips catalyst consists of a chromium oxide in silica gel beads to increase surface area, while the Ziegler nanocatalyst consists of an aluminium attached to organic products. The process we'll be looking at is a gas phase process. This reactor consists of mixing hydrogen and ethene being pumped into a fluid bed reactor. This is where the catalysts are placed in a chamber and are contacted with a stationary catalyst. The ethene is polymerized upon contact with the Phillips catalyst inside the chamber, and the products are then separated from the catalyst and extruded into pellets or powder. Any excess ethene is cooled down as the process is exothermic and is recycled into the process again. That's about it. Thanks for watching.